Hello there and welcome to the Sleepy Cosmos channel. Tonight we are not traveling to places that are large and bright and obvious. Tonight we are going somewhere quieter. Somewhere that requires a softer kind of attention. We are going to the places where stars end. Not in catastrophe, though some endings are catastrophic. Not in darkness, though darkness eventually comes for all of them. But in transformation, in the strange, patient, almost unbearably beautiful process by which a star that has burned for millions or billions of years becomes something new, something smaller than you might expect, something denser than imagination can easily hold, something that in its quieter way is more extreme, more astonishing, and more revealing about the nature of the universe than anything that burns. These are the dead stars, and despite the word dead, they are far from still. Some of them spin, some of them pulse with such regularity that they have been used as clocks. Some of them are so magnetic that they would rearrange the atoms in your body if you came within 1,000 kilometers. Some of them will dance slowly around a companion for billions of years, pulling material from their partner's surface until one final act of accumulation tips them over an edge, and then the light from that moment can outshine an entire galaxy for weeks. These are the universe's smallest giants. And tonight, very gently, very slowly, we are going to visit them. If you enjoy these slow journeys through the cosmos and through the deep quiet of space, I want to invite you now to like this video and subscribe to the channel, or leave a small thought in the comments below. It helps other tired people find their way here, one sleepy soul at a time. There are more journeys waiting for you here, through oceans and ancient histories, and the far unlit corners of the universe. But for now, simply settle in. Let your body feel the weight of the surface beneath you. Let your shoulders drop just a little. Let your breathing slow to its own natural rhythm. You don't need to do anything with what you hear tonight, except let it wash over you. This is a journey you take by letting go. Let's begin. Before we can understand how stars die, we need to spend a moment with how they live, because the death of a star is always shaped by the life it led, and a star's life is, at its heart, a negotiation between two enormous forces that push in opposite directions. The first force is gravity. Gravity wants to pull everything inward. It is patient and relentless, and it never takes a day off. Every atom in a star feels the gravitational pull of every other atom. And if gravity had its way entirely, a star would collapse into nothing in a matter of minutes. But it does not have its way entirely, because the second force pushes back. At the core of every star, nuclear fusion takes place. Hydrogen atoms are pressed so close together by gravity that they overcome their natural repulsion and fuse into helium. And in that fusion, a tiny fraction of their mass is converted into energy that pours outward in the form of light and heat and radiation. That outward pressure is what holds the star up. It is what keeps gravity at bay. For a while, the negotiation between gravity and fusion is the whole story of a star's life. As long as the star has fuel, as long as fusion can continue at its core, the balance holds. The star shines. Planets orbit it. Life, perhaps, takes root in the right conditions and the right distances. And for a star like our sun, this balance holds for about 10 billion years. 10 billion years of stable, generous, life-giving light. But the field is not infinite. Nothing is infinite except the patience of the universe itself. And eventually, the hydrogen at the core runs low, the fusion slows, the outward pressure drops, gravity presses a little harder, and the star begins to change. What happens next depends entirely on how massive the star was to begin with. Mass is destiny in the universe of stars. A low-mass star and a high-mass star will have entirely different deaths, entirely different afterlives, and tonight we will visit both. Our sun is a medium-sized star, nothing exceptional by cosmic standards, but for the purposes of what happens at the end of its life, its mass matters enormously. In about 5 billion years, the hydrogen at the sun's core will run low. The core will begin to contract under gravity. And as it contracts, it heats up. That extra heat ignites a shell of hydrogen around the exhausted core, and the fusion there releases so much energy that the outer layers of the sun expand enormously. The sun will swell outward. It will become what is called a red giant. Its outer atmosphere will expand so far that it will engulf the inner planets. Mercury will disappear into the sun's body. Venus will disappear. Whether Earth is engulfed depends on details of the timing that we cannot yet calculate precisely, but either way, the oceans will have long since boiled away. The surface of the Earth will have been sterilized for billions of years before the red giant phase even begins. None of this is a reason to worry. These timescales are so vast that the human mind genuinely cannot hold them comfortably. 5 billion years is longer than the Earth has currently existed. It is longer than it took for life to arise on Earth, to diversify into millions of forms, to produce creatures capable of lying awake at night, wondering about the death of stars. 5 billion years from now, the word tonight will have no meaning in any language currently spoken. So hold these facts lightly. They are not warnings. They are just the shape of things at enormous scales. And enormous scales, looked at in the right state of mind, are very restful. As the red giant phase progresses, the sun will shed its outer layers, not all at once, not in an explosion, but in a slow, beautiful, gradual unraveling. The outer atmosphere will drift outward into space as a cloud of glowing gas called a planetary nebula. The name is misleading. These nebulae have nothing to do with planets. Early astronomers looked at them through their telescopes and thought they resembled the disks of planets, and the name stuck. But what they actually are is something far more magnificent. They are the dying breath of a star, a shell of gas expanding outward at tens of kilometers per second, lit from within by the hot core left behind. The colors in a planetary nebula depend on what elements are present and how energetic the radiation is from the central remnant. Some are red and orange from hydrogen and nitrogen. Some are blue and green from oxygen. Some show all of these in concentric shells, each one a record of a different phase in the star's outer life. From the right distance, in the right state of mind, a planetary nebula looks like a flower. It looks like the most patient flower in the universe, one that took millions of years to bloom and will take millions more to fade. The Helix Nebula, about 650 light-years away, is sometimes called the Eye of God because it looks, in photographs, like an enormous eye, a ring of glowing gas with a bright center, staring out across space with an expression of complete and total calm. You could look at it for a very long time. You could let it look back at you. And in the center of every one of these glowing clouds of expelled gas, something small and dense and extraordinary has been left behind. This is the first of the dead stars we will visit tonight. The white dwarf. A white dwarf is the exposed core of a star like our sun, when the outer layers drift away in the planetary nebula. What remains is the carbon and oxygen core that was once the furnace at the heart of the red giant. This core is no longer fusing elements. The temperatures and pressures required to fuse carbon are simply not present. The fusion has stopped. The negotiation between gravity and fusion has been permanently decided in gravity's favor, but the white dwarf does not collapse entirely because a new force steps in to resist gravity. Not fusion this time, something quieter and stranger, something that comes from the rules of quantum mechanics, the set of laws that govern how matter behaves at the very small scale. Electrons, the tiny particles that orbit atomic nuclei, obey a rule called the Pauli exclusion principle. This rule states that no two electrons can occupy the same quantum state in the same place at the same time. When a white dwarf forms and gravity squeezes the matter tightly, the electrons resist. They push back. Not because they are electrically charged, not because of any force in the conventional sense, but simply because the laws of quantum mechanics will not allow them to be pressed into the same state. This resistance is called electron degeneracy pressure, and it is enough for a white dwarf below a certain mass to hold gravity at bay forever, or rather not forever, for a very long time, a cooling time, because a white dwarf, once formed, does something very simple. It cools. It has no internal energy source, no fusion, no heat being generated. It is simply a very hot, dense object sitting in the cold of space, and it radiates its heat away into the darkness, slowly, very slowly. A white dwarf starts out extremely hot. Surface temperatures can exceed 100,000 degrees Celsius. They glow white, then yellow, then orange, then red, then dimmer and dimmer as the centuries, and then the millennia, and then the billions of years pass. Our universe is currently about 13.8 billion years old. That sounds like a long time, but it is not long enough for any white dwarf to have cooled completely. The oldest white dwarfs in the universe are still warm, still glowing faintly, still radiating the last of their heat into the cold intergalactic dark. Eventually, in a future so remote it defies any comfortable conception, a white dwarf will cool below the point at which it produces any visible light. At this point, it becomes what theorists call a black dwarf, a dark, cold, dense ball of carbon and oxygen hanging in the void, a crystal of stellar matter, silent, invisible, patient in the way that only something with no particular destination can be patient. There are no black dwarfs in the universe yet. The universe has not been around long enough for any white dwarf to have cooled completely. They are a future phenomenon. They exist only in equations and imaginations, these dark stars waiting to be born from the long death of their predecessors. But they will come in time. Everything comes in time, if the scale of time you are willing to consider is large enough. A white dwarf is remarkably small. The Sun, which is about 109 times wider than the Earth, will leave behind a white dwarf roughly the size of the Earth itself. Something that was once large enough that all the planets of the solar system could fit comfortably inside it will be compressed into a sphere only about 12,000 kilometers across. Our Earth is 12,700 kilometers in diameter. The Sun, all of it, the weight of an enormous star compressed to roughly the size of the planet you are lying on right now. In that white dwarf, a teaspoon of material would weigh about 15 tons on Earth, not because the atoms have changed, but because they have been packed so tightly because gravity has squeezed the space between them down to almost nothing that the density becomes almost beyond comprehension. 15 tons per teaspoon, and yet it is one of the less extreme outcomes for a stellar remnant. There are objects far denser than this, objects where even the atoms themselves cannot maintain their structure. We are going to visit one of them now. If a star is significantly more massive than our Sun, its death is not a gentle planetary nebula followed by a quiet white dwarf. It is something entirely different, something that involves one of the most violent events in the observable universe. A supernova, a massive star, one perhaps 8 times or more the mass of our Sun, lives faster than a low-mass star. Larger stars burn hotter, their cores are under more pressure, and fusion happens more quickly. A star with 10 times the mass of the Sun might live for only 20 million years before its fuel begins to run low. 20 million years sounds like a long time, but it is only about a quarter of the time since the dinosaurs went extinct. And when the hydrogen runs out in a massive star, it does not stop. Instead, the core heats up enough to fuse helium. When the helium runs out, the core heats up enough to fuse carbon. Then neon, then oxygen, then silicon. Each step produces less energy than the last and lasts for a shorter time. The hydrogen phase might last millions of years. The helium phase might last hundreds of thousands. The silicon phase lasts about a day. When silicon fuses, the end product is iron, and iron is the end of the road. You cannot extract energy from iron by fusion. Iron is the most stable nucleus. Fusing it requires energy rather than releasing it. So when an iron core forms at the center of a massive star, fusion stops. Immediately, and gravity, which has been held at bay for the entire life of the star, finally wins. The iron core collapses in less than a second, in less than a quarter of a second. The entire core, a mass greater than our Sun, compressed into a sphere just a few tens of kilometers across in the time it takes to blink. The collapse is so sudden and so violent that the outer layers of the star, the vast envelope of gas that was the star's body, fall inward and then bounce off the suddenly rigid core and are blasted outward in an explosion of staggering energy. This is the supernova. A supernova can briefly outshine its entire host galaxy. All 100 billion or more stars in a galaxy, briefly dimmed by the single death cry of one massive star. The energy released is almost too large to name. More energy in a few seconds than our Sun will release in its entire 10 billion year lifetime. Most of it is carried by neutrinos, almost massless particles that pour through the collapsing core in unimaginable numbers. Billions of neutrinos from distant supernovae are passing through your body right now, through the room around you, through the earth beneath you. Without interacting with anything, they are ghosts of stellar death passing through you as you rest. The heavy elements that are forged in the supernova and in the star's life, things like calcium and iron and oxygen and the carbon in your body, are scattered into space by the explosion. They drift outward, they mix with other clouds of gas and dust, and billions of years later, in some of those clouds, new stars form, new planets condense, and perhaps on one of those planets, creatures arise who are made of the scattered remnants of ancient stellar deaths, and who lie awake at night looking up at a sky full of stars and wondering where they came from. You are made of dead stars. Every atom of calcium in your bones, every atom of iron in your blood, every atom of oxygen, and every breath you have taken tonight was forged in the core of a star that died before the sun was born. You are not looking at the stars, you are looking at your relatives. At the center of the supernova explosion, something has been left behind. The collapsed iron core, but by now it is no longer made of iron. The densities and temperatures at the moment of collapse are so extreme that the electrons and protons in the atoms are forced together. Electrons and protons combine to form neutrons. The whole core becomes, in fractions of a second, a ball of neutrons packed together with almost no space between them. This object is called a neutron star, and it is the second dead star we will visit tonight, and it is considerably stranger than a white dwarf. A neutron star is typically about 20 kilometers across. 20 kilometers. You could drive across one in about 12 minutes on a highway with no traffic, but in those 20 kilometers, it contains between 1 and 2 times the mass of our entire sun. A teaspoon of neutron star material would weigh roughly 4 billion tons on Earth. 4 billion tons in a teaspoon, not 15 tons like a white dwarf. 4 billion tons. The difference in density between a white dwarf and a neutron star is roughly the difference between a feather and a mountain. A neutron star is so dense that the laws of physics that describe matter in everyday conditions are no longer adequate to describe what is happening inside it. We need quantum mechanics and general relativity both simultaneously pressed together in equations that even physicists find challenging. The interior of a neutron star may contain states of matter that do not exist anywhere else in the observable universe. Some theorists believe the innermost core may contain strange quarks, particles that do not normally exist freely. Some believe it may contain a superfluid of neutrons flowing without friction through the star's interior. A river of quantum liquid miles beneath a surface of crystalline neutron-rich nuclei. We genuinely do not know what is at the center of a neutron star. It is one of the great unanswered questions in all of physics. And the not knowing is not a failure, it is an invitation. An open door that experiments and observations are slowly, patiently pushing. Now, if you are still with me, I want to pause here for just a moment. We are somewhere in the middle of this journey tonight, and I want to invite you to notice how you feel right now. Your body is resting. Your breathing has probably slowed since we began. The thoughts that felt urgent a few hours ago are quieter now. That is the whole point of these journeys. If this is your first time finding this channel, I want you to know that there are many more evenings like this one waiting for you here. More slow journeys through the cosmos and through history and through the natural world's quietest corners. You can find them by subscribing to this channel, and they will be there whenever you need a place to rest your mind. You can do that now, or you can simply keep resting. Either way, I am glad you are here. Now, let's go back to the neutron stars, because we have only just begun to understand what they can do. When a neutron star forms in a supernova, it inherits two things from the star that made it. It inherits the star's magnetic field, and it inherits the star's rotation. Both of these are amplified enormously by the collapse. Conservation of angular momentum means that as the core shrinks, it spins faster, much faster. A stellar core that might have rotated once every few weeks will, after collapsing to neutron star size, rotate hundreds of times per second. Imagine taking something the size of the sun and shrinking it to something the size of a city while conserving all the spin. The result is a neutron star that rotates with almost unimaginable speed. Some newly formed neutron stars rotate more than 700 times every second, 700 full rotations per second. An object the size of a city, with twice the mass of the sun, spinning 700 times per second. It is difficult to hold this image in the mind without feeling something like vertigo. And the magnetic field. A neutron star's magnetic field is also amplified by the collapse. The magnetic field of a typical neutron star is roughly 1 trillion times stronger than Earth's magnetic field. 1 trillion times. At this field's strength, atoms behave in ways that are completely alien to anything we encounter in everyday life. The electron clouds around atoms are distorted into long, thin cylinders aligned along the magnetic field lines. Chemistry as we know it becomes impossible. Biology as we know it becomes impossible. If a neutron star with a typical magnetic field were where our moon is, its magnetic influence would be detectable on Earth. And some neutron stars have magnetic fields 1,000 times stronger even than that. These extreme objects have a name. They are called magnetars, and we will visit them in a moment. But first, let's talk about pulsars. A pulsar is a neutron star that we observe doing something remarkable. As a neutron star spins, its intense magnetic field channels radiation out along the magnetic poles. These poles are not necessarily aligned with the rotation axis, just as Earth's magnetic poles are not quite at the geographic poles. So the beams of radiation sweep around like lighthouse beams. If the Earth happens to lie in the path of one of those sweeping beams, we detect a pulse of radiation every time the beam crosses our line of sight. The neutron star is pulsing. A pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish at Cambridge. The pulses were so regular, so precise, so unlike anything previously observed in nature, that the scientists briefly considered the possibility that they were artificial, that they might be a signal from an intelligent civilization. They labeled the source LGM-1. GM stood for Little Green Men. The idea was quickly ruled out, and the explanation of a rotating neutron star was established. But it is a lovely detail in the history of astronomy. The first dead star we ever detected was so strange that for a brief moment we wondered if someone was trying to talk to us. Pulsars are remarkable clocks. The best millisecond pulsars, neutron stars that have been spun up to extremely high rotation rates by accreting matter from a companion star, are so regular in their pulsing that they rival atomic clocks in precision. They are used to test general relativity. They are used to search for gravitational waves from supermassive black holes. Some researchers have proposed using arrays of pulsars as a galactic positioning system for deep space navigation. The dead remnant of a stellar catastrophe spinning hundreds of times a second in the cold dark of space has become one of the most precise tools in all of physics, dead stars doing work. It is one of the more quietly remarkable things about this universe. You can imagine the pulsar from a distance. A tiny, dark sphere, only about 20 kilometers across. You would not be able to see it directly, even if you were close enough, because it is small and the universe is dark. But the beams give it away. Every fraction of a second, twin beams of radio waves and X-rays sweep across the sky. If you were in their path, you would detect a precise and rhythmic pulse of radiation, like a cosmic metronome that has been ticking for millions of years, like the heartbeat of something very small and very dense and very old. The pulsar does not know we are listening. It is simply spinning. It has been spinning since the supernova that made it, and it will keep spinning for far longer than our civilization will exist. It is indifferent in the way that all of nature is indifferent. And yet that indifference can feel in the right mood, like a kind of peace, something that has no agenda, no expectations, something that simply turns. Now we come to the magnetars. If a standard neutron star's magnetic field is extraordinary, a magnetar's is something else entirely. A magnetar is a neutron star with a magnetic field roughly 1,000 times stronger than an ordinary neutron star, which means 1,000,000,000,000 times 1,000 times stronger than Earth's magnetic field, 1,000,000,000,000 times Earth's field. At this field strength, the neutron star's crust, the thin outer layer of crystalline neutron-rich matter, can crack under the stresses of the field. When it cracks, it releases energy, and the energies involved are not subtle. On December 27, 2004, a magnetar about 50,000 light-years away experienced what is called a starquake. The crust of the neutron star cracked, and in about 1/10 of a second, this event released more energy than our sun releases in 100,000 years. In 1/10 of a second. The burst of gamma rays and X-rays that swept across the solar system briefly ionized part of Earth's upper atmosphere. From 50,000 light-years away, it was detectable on Earth despite being at the other side of the galaxy, because it was so luminous that it briefly saturated instruments designed to observe much closer and much less energetic events. A crack in the crust of a dead star, 50,000 light-years away, briefly changed the chemistry of the air 60 miles above your head. The dead stars are not entirely quiet. Magnetars also produce what are called fast radio bursts, or at least some of them do. Fast radio bursts are intense, millisecond-long bursts of radio waves that were first discovered in 2007 and for years remained completely mysterious. They appeared to come from all directions in the sky. They were so brief and so bright that they seemed almost impossible. An enormous amount of energy, enough to power the sun for decades, released in a millisecond. Where could such a burst come from? The leading explanation now involves magnetars, a cracking magnetar crust or some energetic rearrangement of the magnetic field can produce a fast radio burst. We detected one from a magnetar within our own galaxy in 2020, which helped confirm the connection. But we still do not fully understand all the details. The universe keeps its fastest secrets close. It reveals them slowly through instruments and patience and the steady accumulation of observations taken over years and decades. It requires us to be in the business of waiting, which tonight you already are. There is another kind of dance that dead stars perform, and it is one of the most dramatic in the cosmos. Many stars exist in binary systems. Two stars born from the same cloud of gas, orbiting their common center of mass for their entire lives. Sometimes both stars in a binary die and leave behind remnants. Two white dwarfs orbiting each other, a white dwarf and a neutron star, two neutron stars. These pairs continue their orbital dance after death, spinning around each other in the cold, radiating gravitational waves and slowly spiraling inward. Gravitational waves are ripples in space-time, predicted by Einstein in his general theory of relativity and directly detected for the first time in 2015. When two massive objects orbit each other, they distort the fabric of space-time around them. As they orbit, they send ripples outward, like the ripples from a stone dropped into still water. Except these ripples travel at the speed of light, and they stretch and compress the very fabric of space as they pass. When two neutron stars orbit each other and radiate gravitational waves, they lose energy, and as they lose energy, their orbit shrinks. They draw closer, they orbit faster, they radiate more waves, which makes them lose energy faster, which makes them closer faster. It is a gentle but inexorable spiral, and it can last for hundreds of millions of years before the final phase, the end spiral. When the two neutron stars are moving so fast and so close that the whole process accelerates to its conclusion in seconds. In August of 2017, two neutron stars spiraled together close enough to be detected by gravitational wave observatories on Earth. The signal lasted about 100 seconds. In those 100 seconds, two objects, each more massive than the Sun and each only about 20 kilometers across, collided at a significant fraction of the speed of light. The collision was also observed across the electromagnetic spectrum, from gamma rays to visible light to radio waves. Astronomers were able to watch it with conventional telescopes, and what they saw in the optical and infrared was a kilonova. A kilonova is an explosion produced by the collision of two neutron stars, and it is remarkable for what it makes. The extreme densities and temperatures in the collision produce neutron-rich conditions that allow heavy elements to be forged. Gold, platinum, iridium, the heavy elements that are too heavy to be made in ordinary stellar fusion. Too heavy even to be made in supernovae in significant quantities. They are made here. In the cataclysmic death dance of two neutron stars, The gold in your jewelry, if you have any, the platinum in any electronic device near you tonight, was made in a kilonova. 2 neutron stars colliding billions of years ago scattered heavy atoms through the galaxy, and some of those atoms ended up in the cloud that became the sun and the earth, and eventually found their way into the hands of jewelers and the circuitry of devices, and eventually your life. The most precious metals on Earth arrived here from the collision of the universe's smallest giants. When a white dwarf is in a binary system with a normal star, something else can happen. Something slower. The white dwarf's gravity can pull material off the surface of its companion. Hydrogen gas streams from the companion's atmosphere onto the surface of the white dwarf. It accumulates there, layer by layer, very slowly, over thousands and millions of years. As the layer builds up, the temperature and pressure at the base of the accumulation climb higher and higher until they reach the threshold for nuclear fusion. And then the hydrogen detonates in a surface explosion called a nova, not a supernova, just a nova. The brightness can increase by a factor of thousands in a matter of hours. A star that was previously invisible to the naked eye can suddenly appear in the sky as one of the brightest objects visible. Ancient sky watchers noticed these appearances and called them new stars, which is where the word nova comes from. The explosion blows the accumulated hydrogen off the surface of the white dwarf, but the white dwarf itself survives. And then the accumulation begins again, the same slow gathering of hydrogen, the same gradual buildup, the same eventual detonation. A nova system can repeat over and over across millions of years, a patient, periodic brightening in the sky driven by the slow hunger of a dead star. But there is a limit to how much mass a white dwarf can hold. A white dwarf is supported against gravity by electron degeneracy pressure, and in 1930, a young Indian physicist named Subrahmanyan Chandrasekhar, traveling by ship from India to England at the age of 19, worked out the mathematics of this on the voyage. He showed that there is a maximum mass for a white dwarf. Above about 1.4 times the mass of our Sun, electron degeneracy pressure is no longer sufficient to resist gravity. Above this mass, which we now call the Chandrasekhar limit in his honor, a white dwarf will collapse. And when it collapses, the entire star, not just a core, but the whole white dwarf, detonates in a thermonuclear explosion. A Type 1a supernova. Type 1a supernovae are extraordinary for several reasons. First, they are extraordinarily bright. For a few weeks, a single Type 1a supernova can outshine its entire host galaxy, billions of stars, all outshone by one. Second, and perhaps more importantly for cosmology, they all have approximately the same intrinsic brightness. Because they all involve white dwarfs of approximately the same mass, the Chandrasekhar limit, detonating in the same kind of thermonuclear event. This makes them what astronomers call standard candles, if you know how bright something actually is. And you can measure how bright it appears from Earth, you can calculate how far away it must be. Type 1a supernovae let us measure distances across the universe. And in the 1990s, 2 teams of astronomers using Type 1a supernovae to measure distances to very distant galaxies made a discovery that shook cosmology. They discovered that the universe's expansion is accelerating. Distant galaxies are moving away from us faster and faster over time. Something we do not understand and have called dark energy is driving this acceleration. We discovered dark energy, one of the greatest mysteries in all of science, by watching dead stars explode. The universe contains stars of many different masses and ages. When astronomers look at a distant galaxy, they are looking at a population, a community of stars at every stage of the story we have been telling. Some are just forming in their clouds of gas and dust. Some are in the steady middle part of their lives, like our sun. Some are swelling into red giants, and some have already ended and left their remnants behind. White dwarfs and neutron stars distributed through the galaxy like the memories of fires that have gone out. Astronomers classify stars by their color and brightness in a diagram called the Hertzsprung-Russell diagram, after the two astronomers who independently developed it in the early 20th century. In this diagram, stars are not randomly scattered. They fall into patterns. Most stars cluster along a band called the main sequence, the region where stars spend most of their lives while fusion is supplying their energy. Our sun is a main sequence star, a stable, middle-aged, unremarkable member of a very large club. But off to one side of the main sequence, there are the red giants, cooler and larger and older, and tucked in the corner of the diagram, small and faint and very hot, are the white dwarfs, hot but dim. Because dim is what happens when you are small. No matter how hot the surface, a small surface area means a limited total output of light. White dwarfs glow white, yellow, orange, red, progressing through the colors of cooling like embers in a dying fire. Astronomers can watch this progression in real time across populations of white dwarfs in globular clusters, ancient cities of stars that formed early in the galaxy's history. The coolest, reddest white dwarfs in these clusters are the oldest. The hottest, whitest ones are the most recently formed, a whole history of stellar endings spread across a patch of sky like a calendar made of light. The idea of stellar populations was developed by the astronomer Walter Baade during World War II. Working at the Mount Wilson Observatory in California, taking advantage of wartime blackouts that darkened the skies above Los Angeles, Baade was able to resolve individual stars in the Andromeda Galaxy for the first time. He noticed that different regions of the galaxy had different kinds of stars. The spiral arms contained young, hot blue stars. The central bulge and the globular clusters that surrounded it contained older, cooler, redder stars. He called these Population 1 and Population 2. Population 2 stars are the oldest. They formed early in the galaxy's history, when the gas available for star formation was mostly hydrogen and helium, with very little of anything else. They are therefore very low in what astronomers call metals. In astronomical usage, everything heavier than hydrogen and helium is called a metal. This includes oxygen, carbon, iron, and everything else on the periodic table. A Population 2 star has very little of these things, because when it formed, the universe had not yet had enough supernovae to enrich the gas with heavy elements. Population 1 stars, like our sun, are richer in these elements because they formed from gas that had already been enriched by generations of earlier stars living and dying. We are, in a very literal chemical sense, the product of stellar generations that came before us. The sun is a child of dead stars, and so are you. The fate of the universe in the very far future is a subject that cosmologists think about with a mixture of scientific rigor and something that might charitably be called cosmic melancholy. The era we live in, this current age, is sometimes called the stelliferous era, the era of stars. It is expected to last in total for roughly 100 trillion years. 100 trillion years. That is more than 7,000 times the current age of the universe. For the first part of that enormous span, new stars will continue to form from clouds of gas, but the gas is not infinite. Star formation uses it up, and while supernovae return some gas to the interstellar medium, the overall trend is toward depletion. Over time, the rate of star formation will slow. Fewer new stars will be born each billion years. The galaxy will gradually dim as old stars die and are not fully replaced. By the end of the stelliferous era, most of the gas in the galaxy that is capable of forming stars will have been used up. Star formation will cease. The last stars to survive will be the smallest and dimmest, red dwarf stars with masses as low as 1/10 of the sun's mass, which burn so slowly that they can live for 10 trillion years or more. They will outlast everything. By the time the last red dwarf goes out, all the sun-like stars will have become white dwarfs and will be well on their way to becoming black dwarfs. All the massive stars will have long since exploded and left their neutron stars and black holes behind. The galaxy will be dark, not empty, full of dark remnants, invisible, orbiting each other in a galaxy that produces no new light. This is the degenerate era, the age of stellar corpses, and it will last for an almost incomprehensible time, longer than the stelliferous era, much, much longer. In the degenerate era, the occasional collision between white dwarfs or neutron stars will produce a brief flash of light, a kilonova here, a type 1 supernova there, rare sparks in an otherwise dark and cooling galaxy. But these events will become rarer over time as the orbits decay and the remnants drift further apart. Eventually, the galaxy itself will begin to change its shape. Gravitational interactions between stars and stellar remnants will gradually scatter objects out of the galaxy entirely, sending them off into the intergalactic void. Over enormous timescales, the galaxy will evaporate, its contents dispersed across a widening universe. What remains at the center will be the supermassive black hole, growing slowly perhaps from the occasional remnant that falls into it, and eventually, after an incomprehensible span, even the black hole will evaporate through Hawking radiation. And then there will be only photons and particles drifting through an expanding and cooling universe, the last traces of a cosmos that once blazed with the light of 1 trillion stars. But this is so far in the future that contemplating it too seriously is not something the mind was designed for. The mind was designed for the present, for this evening, for this breath. So let the far future rest in the equations where it belongs, and let your mind return to the present, to the warmth of the room around you, to the slow and comfortable rhythm of your breathing. Good. There is one more outcome possible for a massive star's death, the most extreme, the one where even neutron degeneracy pressure is not sufficient to hold gravity at bay. If the collapsing core is above a certain mass, nothing can stop the collapse from continuing indefinitely. Not electron degeneracy, not neutron degeneracy. Nothing, the matter falls inward past any known stable configuration, and the result is a black hole, a region of space-time where the curvature is so extreme that not even light can escape. Black holes are not holes in space, they are objects, extraordinarily dense objects surrounded by a boundary called the event horizon, inside which the gravitational pull is so strong that escape requires traveling faster than light. And since nothing travels faster than light, nothing escapes. We will not go inside a black hole tonight, not because they are frightening, though they can seem that way, but because there is nothing to see there. Not nothing in the familiar sense, not a dark room, but a place where our understanding of physics breaks down completely, where the equations that describe space and time and matter produce infinite answers, which is a mathematician's way of saying we do not have the right equations yet. The inside of a black hole is not a destination, it is an admission of ignorance. And ignorance is not a comfortable place to rest. Instead, let's stay outside. Let's orbit at a safe distance and look at the black hole from where we can still understand things. From outside the event horizon, a black hole looks like nothing, a perfect absence, a region of sky where there are no stars, but it makes itself known through its effects on everything around it. Gas and dust falling toward it are heated to millions of degrees as they spiral inward, and they radiate fiercely in X-rays. Stars near a black hole orbit it with measurable speed, and the shape of those orbits reveals the invisible presence at the center. A black hole does not announce itself with drama. It announces itself through the behavior of everything nearby, through the silences and curves it creates in the fabric of space, through the way light bends around it, creating rings and arcs and distorted images of distant galaxies, through the way time slows as you approach it, so that a clock falling toward a black hole would appear from outside to tick more and more slowly as it neared the event horizon, approaching stillness but never quite reaching it, as though the universe itself is trying to pause before the edge. There is something called Hawking radiation, proposed by the physicist Stephen Hawking in 1974, the quantum mechanical equivalent of a black hole's slow exhale. Due to quantum effects near the event horizon, black holes can radiate energy extremely slowly. A stellar mass black hole radiates at a temperature so close to absolute zero that it is indistinguishable from zero by any instrument we could currently build. But over time, over truly astronomical time, far longer than the current age of the universe, a black hole will lose mass through Hawking radiation. It will shrink, it will become smaller and hotter and radiate faster, and eventually, in a final burst, it will evaporate completely. Even the most extreme dead star, even the object that swallows light, is not permanent. Even a black hole will eventually fade. Everything at the right scale of time is temporary, and in a strange way, that temporariness is restful. It means nothing is required to last forever. Not a star, not a black hole, not a thought you are having right now that seems more important than sleep. There are black holes at the centers of most large galaxies. Supermassive black holes, not the stellar mass ones we have been discussing, which form from the death of individual stars, but objects millions or billions of times more massive than the sun. The one at the center of our own galaxy, the Milky Way, is about 4 million times the mass of the Sun. It sits at the galaxy's center, approximately 26,000 light-years away. Tonight, as you rest, it is there in the direction of the constellation Sagittarius, invisible behind clouds of dust, but detectable through the orbits of the stars around it. Those stars move so fast, some of them completing a full orbit around the central black hole in just a few decades, that there is no other explanation for the gravity driving them. Something with the mass of 4 million suns sits at the center of our galaxy, and it is silent, quiescent, doing nothing dramatic for now, just sitting there, massive and patient, occasionally pulling in a cloud of gas that briefly illuminates in X-rays before disappearing past the event horizon. The center of our galaxy is a quiet place as these things go, which is fortunate for us. For most of human history, we could only observe the universe by collecting the light that reached our eyes, and light is only one small slice of the electromagnetic spectrum. The universe communicates in radio waves and microwaves and infrared and ultraviolet and X-rays and gamma rays, all of them carrying information, all of them telling a different part of the story, and almost all of the most dramatic messages from the universe, from its most extreme and energetic events, arrive not in visible light, but in X-rays and gamma rays. Dead stars, it turns out, are among the loudest objects in the X-ray sky. X-ray astronomy began in earnest in the 1960s, when rockets and later satellites could carry detectors above Earth's absorbing atmosphere. And the X-ray sky turned out to be remarkable. Regions of the sky that appeared empty or unremarkable in visible light blazed with X-ray emission. The most powerful X-ray sources in the sky, other than the sun, were often compact objects. Neutron stars and black holes in binary systems, pulling material from a companion and heating it to millions of degrees as it spirals inward. These are called X-ray binaries, and they come in two main flavors: low-mass X-ray binaries, where the companion is a star like our sun, and high-mass X-ray binaries, where the companion is a massive and luminous star whose powerful wind supplies material to the compact object. In both cases, the physics is the same. Gas falls toward the compact object. Conservation of angular momentum turns its infall into a spiral. The spiraling gas forms a disk, an accretion disk. Friction in the disk heats the gas, and the inner parts of the disk closest to the neutron star or black hole reach temperatures of millions or tens of millions of degrees. At those temperatures, the gas radiates in X-rays, bright, flickering, variably intense X-rays that convey information about the extreme conditions at the innermost edge of the disk, where matter is making its final approach toward the compact object. Astronomers can use the timing of this X-ray emission, the flickering patterns, and the quasi-periodic oscillations to measure the spin of the compact object, the curvature of spacetime near it, and even the size of the innermost stable orbit around it. They are reading the gravitational field of a dead star the way a doctor reads a pulse, finding information in the rhythm of something invisible. One of the most celebrated results in modern astrophysics was the first direct image of a black hole's shadow, not an artist's impression, not a simulation, an actual observation, a real image made from real light. In April 2019, the Event Horizon Telescope collaboration, a network of radio telescope arrays around the world linked together to function as a single Earth-sized telescope, released the first image of the black hole at the center of the galaxy M87, about 55 million light-years away. The image showed a bright ring of glowing gas surrounding a dark central region. The dark region was the black hole's shadow, the zone from which no light could escape. The bright ring was light from the accretion disk, bent around the black hole by its enormous gravity, some of it completing full circles around the event horizon before escaping outward and reaching our telescopes. The image was blurry by the standards of modern photography. It was a circle of orange light with a dark center, roughly the resolution of reading a newspaper from the surface of the moon. But it was an image of something we had never imaged before, a region of space-time from which light cannot escape, made visible by the light that escaped from just outside it. The team then released an image of the black hole at the center of our own galaxy, Sagittarius A star, in 2022. It looked similar, an orange glow around a dark center, but it was in our own galaxy, 26,000 light-years away, and it had been imaged by the combined effort of telescopes on multiple continents, working together like a single instrument with the diameter of the Earth. Human ingenuity, spread across the planet, focused on a single point 26,000 light-years away to take a picture of a shadow, the shadow of something from which light cannot escape. And the picture came out beautiful, orange and warm and almost gentle looking, as though the most extreme object in the local universe had agreed to sit still for a portrait and had dressed in its nicest colors for the occasion. Gravitational wave astronomy is still young and already revolutionary. Before 2015, we had never directly detected a gravitational wave. We knew they existed because we had seen their effects. The orbital decay of binary pulsars matched the predictions of general relativity for energy loss to gravitational wave emission with extraordinary precision, earning a Nobel Prize in 1993. But we had never felt a gravitational wave pass through our instruments, never felt space-time ripple. In September 2015, the LIGO detector in the United States detected the first direct gravitational wave signal. It lasted about 1/5 of a second, and it came from two black holes spiraling together and merging about 1.3 billion light-years away. Two black holes, each several tens of times the mass of the Sun, circling each other at hundreds of kilometers per second, and then merging in a final fraction of a second that converted an amount of mass equivalent to several suns entirely into gravitational wave energy. The peak power of the event was roughly 50 times the combined light output of every star in the observable universe, released in gravitational waves in about 1/5 of a second. And on Earth, the resulting spacetime ripple stretched and compressed the 4-kilometer arms of the LIGO detector by about 1,000th the diameter of a proton, less than the width of a single proton. That was detectable. That tiny, quiet whisper of spacetime from 1 billion light-years away was detectable, because the instruments were extraordinary, because the scientists were patient, because they had been building and refining and waiting for years, listening for a signal that would last a fraction of a second and carry more energy than the visible universe's light. Patience in astronomy is one of the primary tools of discovery, not just waiting. Careful, prepared, instrument-equipped waiting, the kind of waiting that is indistinguishable from readiness. We have traveled far tonight, further than we can measure in familiar units. We have visited the quiet remnants of stars like our sun. We have stood at the edge of the violence that ends massive stars and seen what is left when the violence subsides. We have listened to the precise, patient ticking of pulsars and felt the impossible intensity of magnetars. We have watched two neutron stars dance together for hundreds of millions of years and collide in a moment of brightness that forged the gold in the world. We have orbited at a respectful distance from regions of space-time where our equations run out and our imagination must take over. And through all of it, the theme has been the same. Matter does not disappear, it transforms. A star's death is not an ending, it is a redistribution, a reshaping. The atoms that were in that star go somewhere. They become gas clouds, they become new stars, they become planets. They become the bodies of creatures who look up at the night sky and feel a sense of recognition they cannot quite explain. The carbon in your body was made in a star. The iron in your blood was scattered by a supernova. The gold in the world arrived from a kilonova, two neutron stars giving everything they had in a moment of impossible brightness. And you, lying here in the dark, breathing slowly, feeling the ordinary weight of the day easing out of your shoulders, you are part of that same story, not a separate observer watching the universe happen. You are an expression of it, made from the same stuff as the stars, subject to the same laws, bound by the same gravity, warmed by the same kind of fusion that lights every sun and every galaxy in the observable universe. You are not outside the cosmos looking in. You are inside it, completely, intimately, inescapably, inside. And right now, at this moment, you are doing what the universe has always done when conditions allow. You are resting. The stars above you tonight, the ones visible through whatever darkness surrounds you, are not only lights, they are processes, negotiations between gravity and fusion, playing out across timescales that dwarf the whole of human history. Some of them are young and will burn for billions of years yet. Some are in their red giant phases right now, swelling slowly outward as we watch, or rather as we would watch if we had instruments sensitive enough to see the change. Some have already ended. Some of those points of light you see are white dwarfs, visible only because they are still warm, still radiating the last of their heat into the dark. Some are neutron stars, detected by instruments we cannot see with, spinning in their precise and patient ways. And some of those points of light are so far away that the light reaching your eyes tonight left those stars before the earth existed, before the sun existed. You are looking at ancient history with every glance upward. The sky is not a ceiling, it is a window that looks in multiple directions simultaneously, outward in space and backward in time. And behind every point of light, eventually, there is a death and a transformation and a new kind of smallness that is, in its way, the most extraordinary kind of greatness. If you could hear the universe, it would sound different from silence. Astronomers often convert the signals they receive, the radio waves, the X-rays, the gravitational waves, into sound, a process called sonification, shifting the frequencies of the universe's signals into the range our ears can detect. And what they find is that the universe is not quiet. The Milky Way's center, sonified from X-ray and radio data, sounds like something between wind and music. The remnant of the Cassiopeia A supernova, the expanding shell of gas left by a stellar explosion about 300 years ago, has been sonified and sounds like a vast and eerie chord, rising and shifting in pitch as different regions of the remnant are heard. The pillars of creation, those enormous columns of gas and dust in the Eagle Nebula, where new stars are forming, have been sonified from infrared and X-ray data and sound like a breath being drawn in. The universe, listened to through these translated ears, sounds like it is breathing, slowly and enormously and without hurry, like something very large that is simply going about its business, indifferent and magnificent. Like the breathing of something that has no reason to rush. Night, the gravitational wave signal from the first detected black hole merger was sonified and released to the public. When you speed up the signal and shift it into audio frequencies, it sounds like a brief chirp, a rising glide of tone that sweeps upward and then cuts off. That chirp is the sound of two black holes, each dozens of times the mass of the sun, spiraling together and merging. Two objects that between them contain more mass than any star alive today, colliding at a significant fraction of the speed of light from 1 billion light years away. And what reaches us is a chirp, a small, brief, almost delicate sound. The universe, in its extremity, communicates with a whisper. That chirp is one of the most important sounds in the history of science, and it lasts less than a second. And if you are the kind of person who finds comfort in small things that carry enormous weight, tonight seems like a good night to find it, in the light, from the most distant things we can see, left its source before the Earth existed. The oldest light in the universe, the cosmic microwave background, is not light from stars at all, but from the moment. About 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light was able to travel freely for the first time. Before that moment, the universe was so hot and dense that photons could not travel more than a short distance before being absorbed and re-emitted. The universe was opaque, a fog of plasma so bright that there was no darkness anywhere, but also nothing you could call a view, just light bouncing endlessly through a dense and glowing medium. And then, as the temperature dropped, the fog lifted, atoms formed, and light poured outward. It has been traveling ever since, 13.4 billion years, and it is still reaching us now. It is just very cold. The expansion of the universe has stretched its wavelengths until it is cooled from the hot glow of the early universe to a temperature of just 2.7 degrees above absolute zero. It arrives at our microwave detectors as a faint isotropic glow, the same in all directions. The afterglow of the universe's beginning, the oldest light there is, 13.4 billion years old, and some of it is reaching you right now, not detectably, not without instruments, but the cosmic microwave background fills all of space, including the space the room you are in right now. The universe's oldest light is passing through you as you lie here in the dark. Everything is passing through everything. Neutrinos from supernovae, gravitational waves from merging black holes, the cosmic microwave background from the dawn of time. The universe is extraordinarily permeable. We are extraordinarily transparent to most of what it sends. And yet we are here, and it is here. And tonight they share the same space and the same quiet and let that thought drift away now. Let it float upward like the planetary nebula of an old star, spreading gently outward, becoming diffuse, becoming part of the background. You do not need to hold it. You do not need to remember it. It has already done its work. It has made the dark a little larger and the universe a little more present, and the sense of urgency that days can create a little smaller. Because from the perspective of a neutron star spinning 700 times a second in the cold between galaxies, there is very little that requires your immediate attention tonight. Everything that needs to be done will still need to be done in the morning, and you will do it better having rested. The dead stars know this. They have all the patience in the universe, and they are lending it to you tonight. Your breathing is slow. Your body is heavy in the comfortable way. The weight of the bed or the chair beneath you is solid and reliable and has been there all along. The room is quiet. Or, if it is not quiet, the sounds in it are familiar and safe. They are the sounds of your life. And your life is a good place to be right now. Tomorrow will have its own weight and its own demands, but tonight belongs to rest. Tonight belongs to the slow drift of neutron stars cooling in the dark, to the patient rotation of pulsars that will still be spinning when the sun has become a white dwarf and cooled to nothing, to the long, silent dance of binary systems spiraling slowly toward a moment of extraordinary light. Tonight belongs to everything that is too slow to rush, everything that unfolds on a timescale that includes sleep. Close your eyes if they are not already closed. Let the darkness behind them be the darkness of space, clean and cold and enormous, and in that darkness somewhere, a pulsar is ticking. 100 milliseconds, 100 milliseconds, 100 milliseconds. So precise that the tick itself is like a lullaby, something that has been going on since long before you were born and will continue long after. A heartbeat of the dead universe. Slow now. Steady, reliable, you can rest alongside it. You can let the rhythm of that distant spinning settle into your own breathing. In out, slower, a little slower. Good, let the magnetar be far away. Let its enormous field reshape the atoms in some distant part of the galaxy while you remain here, warm and safe and at the right distance from everything dangerous. Let the neutron stars dance in their long spiraling orbits. Let the white dwarfs cool in their geological silence. Let the black holes hold their mysteries behind their horizons while the stars outside them go on orbiting in patient circles. Let all of it go on without you for a few hours. The universe will manage. It has been managing for 13.8 billion years without your attention. It will be fine tonight. You are made of dead stars, and you are alive. That is the most extraordinary thing in the observable universe. Nothing else we know of has managed it. Nothing else takes atoms forged in stellar cores and organizes them into something that can wonder where it came from. something that can lie in the dark and feel the weight of questions and decide, tonight at least, to let the questions rest. You are a temporary arrangement of stellar matter that has achieved consciousness, and consciousness tonight is choosing sleep. That is not giving up. That is wisdom. The stars would do the same if they could. Tonight we visited the universe's smallest giants. We met white dwarfs, dense and patient, cooling across billions of years. We stood near neutron stars, the most exotic matter we know how to find, spinning and pulsing and singing in radio waves. We felt at a safe distance the incomprehensible field of a magnetar. We watched binary stars spiral together across geological time and collide in a moment that wrote the periodic table in gold. We circled the silence of a black hole and felt what it means to reach the edge of understanding. We listened to the universe's chirps and whispers. We felt the oldest light in existence passing through us. And we came home, back to the small and the warm and the breathing, back to the only place in the solar system where, tonight, someone is making tea, someone is reading by lamplight, where someone is putting a child to sleep, and someone is lying very still and breathing very slowly and letting the dead stars do their ancient patient work while sleep arrives on its own schedule, which is always just when it is needed. There is something the dead stars can teach us if we are willing to take the lesson in the quiet way it is offered. Not an urgency, not in the language of productivity or achievement, but in the language of time. A white dwarf cooling over billions of years is not in a hurry. A pulsar ticking away at its precise and patient interval is not measuring anything against a deadline. A neutron star spinning in the cold dark of the galaxy is not waiting to be noticed or evaluated or remembered. It is simply being what it is, doing what the physics of its situation requires, with complete and total equanimity. And if you can borrow even a fraction of that equanimity tonight, just for the few hours between now and morning, that is enough. You do not need to keep the whole universe in mind. You do not need to remember everything we have visited tonight. All you need is the permission to stop, to be still, to rest. The dead stars grant it, the universe grants it, and the bed beneath you has been granting it all evening. If this journey was good for you tonight, I hope you will come back. There are more journeys through the cosmos and through history and through the world's quieter places, all made for evenings like this one. You can find them by subscribing to this channel, and they will be there whenever you need them. If this helped you rest, please consider leaving a like or sharing it with someone who could use a quiet night. It helps other tired people find their way here, one sleepy soul at a time. Thank you for traveling with me tonight. Thank you for your patience and your willingness to drift. That is a rare and beautiful thing. Now let everything go still. Your breathing is already where it needs to be. Your body already knows what to do. Sleep is not something you have to find. It is already here, at the edges of your awareness, patient as a white dwarf cooling in the dark. You don't need to look for it. You only need to stop looking away from it. So stop, be still. Let the dead stars dance in their distant dark while you rest in yours. Sleep well, and good night. The dead stars are watching over the dark, spinning and cooling and dancing in their ancient patient ways. They were here before you. They will be here after. And tonight, between those two great stretches of time, you are here too. Resting. That is enough. That is everything.